So let's start working on the project. So I have PyCharm here. I created an empty project and I have a data folder inside that project where I keep the MNIST dataset. The first thing I'm going to do is to create a new Python file. I'm going to give it a name network MLB. Let's start by importing the required package. For this we will need NumPy as the main package and other package as well for decompressing and loading the dataset. I will create prepare data function for loading this dataset. Using gzip module, we can open the compressed dataset file. Like many standard datasets, MNIST has three main parts: the training, the validation, and test parts. And each of those contains samples of handwritten digits in image format and the corresponding labels. We use Pickle to load all of them using the right encoding. We will extract the image and labels from each individual segment. But before moving on, I want to make it clear that we are going to use Python's list comprehension extensively in this tutorial. If you are not familiar with list comprehension, it's a very easy and convenient way to create lists. Here is a quick example. The code in the top creates a list using list comprehension, while the bottom one uses a traditional for loop way. The difference in convenience and conciseness is pretty clear. It will also become more obvious as we go through this tutorial. Now back to the prepare data function. We have three variables corresponding to the training, validation, and test segments. Each of them contain two lists. The first one has the image while the second one has the labels. For example, tr data 0 is the list of training image and tr data 1 is the list of training labels. Using list comprehension, we would extract each of them in a separate list and we will call the first one tr inputs. Later, we will use this as the input during the training stage. One important pre-processing step here that we need to do is to flatten the input image to make them compatible with the multi-layer perceptron architectures we have used. So this means that we are converting the 28 by 28 array of each image into a 784 by 1 array. And this can be done easily using a NumPy reshape. Next, we will create the second variable tr labeled for training labels, and again we will use list comprehension in the same way. After this processing, we recombine them in a single variable named training data. And the same steps will be followed for the test and the validation. Thus, prepares data's final output is the three new variables: training data, validation data, and test data. One thing missing from the prepared data function is having the training labels in a format that can be consumed by the network during the training. This format is called one-hot encoding. Specifically, the label is converted into a vector whose length is the number of classes, in this case 10 classes because we have the digits from 0 to 9. All the entries in the vector will be 0 except for the index corresponding to the label, which will be set to 1. So let's create a utility function called onehot to do this job for us. Then we replace the raw label in tr labels with the onehot version. Now we are done with the data preparation. Let's head to the network creation. Let's create a new class called network MLB. I want this class to be initialized through a list whose interest contains the number of neurons in each layer. For example, if I want 3 layers for MNIST classification, I will have a list with 3 values like this one. The first element will be 784 to match the input image, and the last element will be 10 to match the number of classes. Between them, we can have any number of hidden layers with arbitrary number of neurons, but here I have fixed it to one hidden layer with 30 neurons. I will call our initialization list as sizes. For each neuron in our network, we need a bias, as shown in this illustration. Note that the first layer will be excluded because it's the actual input. Let's create biases list with one entry for each layer, going from the second to the last. Each entry will be a vector whose first dimension is the number of neurons in the layer. And we will use NumPy round-in to put some initial random values. Now let's turn to weights. Similar to biases, we will have them in a list from layer number 2 to the last layer. The difference is that each element is a two-dimensional matrix. The dimensions match the number of neurons in the previous and the current layer respectively. We have it in this way because our network is MLB, also called a fully connected network, meaning each neuron in a layer is connected to all neurons in the previous layer. Again, we will use random initializations for the weights as well. Next, we create the feedforward function. This function produces the network's prediction for a specific input by simply applying the perceptron equation you see here for each neuron or perceptron in the network. The following figures make it easy to comprehend. For an input sample, we perform a dot product between the first set of weights and the input, an operation that's equivalent to performing the weighted sum on the input. This will be followed by adding the bias values, and then finally we apply an on-layer activation function sigma. The output, called the activation, will be used as an input to the next layer, and this process continues in the same way till the final layer. To implement this, we will have variable A as an input. It's also the initial activation. We will iterate over the biases and weights, and we will calculate the new activation as the sigmoid of the dot product of W and A after adding B. The last activation will be returned as the output. We need also to define the sigmoid function. It is a nonlinearity that we consider here, but of course you can consider other function. The sigmoid of A is just 1 divided by 1 plus e to the power of minus A. In our class, we will also need a way to test the performance of the network after the training is completed. So we will create evaluate function. The input will be test examples and the corresponding true predictions, also called the ground truth. We will have both of them in test data variable. Each element in test data is a tuple x and y, where x is the input image and y is the true label. So the network predictions on x can be acquired by applying the feedforward function we just created. Remember that our network produces a one-hot encoded vectors of length 10. So to recover a single final prediction from this vector, we bin the index with the largest activation value through NumPy argmax. Now we have the network predictions and the true labels paired together in a variable test results. All we need to do is to count the number of times the predictions equal the true label, and this will be the accuracy estimate. Before we can use our network for evaluation, we need to implement the training method. This particular part requires proper understanding of the backpropagation algorithm, which will be discussed in the next part. For now, I will import the backpropagation code with minimal changes to the current class. This gives us a quick way to test the code we wrote on the dataset. So I will create another class called trainable network that will have the backpropagation functions. This class will be used as a superclass of our network MLB, and thus all the functions we have here can be used in network MLB. And the main training function is SGD, or stochastic gradient descent. As a bit of refactoring, I will remove the sigmoid function we created earlier and put it in this class. Also, I will define sigmoid prime. This is a derivative of the sigmoid function and it is needed by SGD. Now let's import trainable network in network MLB. Also replace the old sigmoid. And now we are ready to test our network. First, we get the dataset segments using a prepared data function. Then we create the network. To be able to use SGD, we need to set the superclass of network MLB as trainable network. The SGD function takes the training data as the first parameter, which is the most important parameter of this function. The next parameter is the number of epochs, and you can think of this parameter as the times we go over the whole training data set as we train the network. This is followed by the batch size and the learning rate, and these will be explained later. And finally, some validation data that can be used to evaluate the progress of the network training. Once the training is done, we can call the evaluate function on some unseen data and print the accuracy. Now let's run this. As you can see, after each epoch, we print the accuracy as a number of correct predictions out of 10,000, which is the number of samples we have in the validation segment. The last line shows the accuracy on the unseen data as 93.7%, which is pretty decent considering that we are using a basic feed-forward architecture here.